Hello everybody and welcome to AstroFest 2021. This year we've gone worldwide. My name's Lucy Green and along with Stuart Clark we'll be your hosts this evening. And actually we've turned the pandemic lockdown to our advantage because we're able to be celebrating this evening, hopefully fingers crossed, the landing of another rover on the surface of Mars. And we have a fantastic set of speakers lined up to guide us towards that moment in time. And tonight you can ask us questions, you can ask the speakers questions. So Stuart, tell us how audience members can do that.
Yes, it's lovely to be back with you. I'm so sorry that we're not all together in Kensington like we usually are. But as Lucy says, we're going to turn this to our advantage and bring you some, truly fantastic speakers starting tonight. And it's your chance to ask questions of them as well. So on your Zoom window that you've got, you should be able to see a Q&A button there. If you press that, you'll be able to type in your question, and then we'll be asking our questions to our guests at various different times throughout the evening. So just pop your question in there whenever it occurs to you. And I can see already that some of you are going. You're very keen, and this is why we love an AstroFest audience. Well, we're going to start our discussion of Mars this evening, not with NASA's Perseverance rover. Believe me, we'll be talking about that an awful lot this evening. But NASA's not the only country that's going to Mars. And last week, the United Arab Emirates achieved orbit around the Red Planet at their very first attempt with the Emirates Mars mission. And it's such a pleasure because tonight our first guest is Omran Sharaf. He's the project director of the Emirates Mars mission at the Mohammed bin Rashid Space Center. He and his team are responsible for developing, launching and operating the mission and its HOPE probe. So Omran, welcome to Worldwide AstroFest. I know it's very late where you are, so a very big thank you for you joining us this evening. We really appreciate it. And firstly, congratulations on getting to Mars on your first attempt. Tell me about that Mars orbit insertion maneuver. From your perspective, how did it feel to be waiting and watching for the confirmation?
First of all, thank you very much for having me with you. It's an honor to be with you, I have to say. And don't worry about it being late, because actually I was going to stay up anyways to watch Perseverance arrival on the surface of Mars. So it's an exciting day, a day that we all look forward to and wish our colleagues and friends at the United States and at NASA the best, at JPL also the best. So looking forward to the results. Going back to your questions regarding actually the day of arrival and the feeling, it's a question that I got asked a lot, I have to say, and I got a lot of mixed feelings on that day, even the days before that. It was a mix of being proud, happy, extremely stressed, confident, scared, at some point terrified, but still confident. So it was a weird feeling, mix of feelings at that moment. And the moment that we started the Mars orbit insertion, and we actually received the telemetries confirming that it started. And I had to wait for 11 minutes to verify that, since there was 11 minutes of delay around that time. It was a good feeling to see the signal, but at the same time, the team started their initial poll to check the status of the spacecraft and the subsystems. And every time I was hearing the team, on our TeamSpeak system, and as I can hear the team talking about their subsystem and saying, okay, this is nominal, this is nominal, I felt relieved, I have to say. But then as we went through, let's be very honest, things started well, but then you never know how things would end. So it was a very interesting experience. It's the first time we send a deep space mission. It's the first time we send a mission to Mars. So as a whole team, we were never exposed to something like this before. So it was a learning experience for us, even on the day of arrival. Until this day, we're speaking on today, I'm learning every single day. As a project director, I'm learning. my team also is learning. It's amazing how much we learned over the past 7 years. And people thought that the 7 months of cruise would be a quiet time, but it wasn't. It was busy learning, and learning.
Yes, yeah, it's an extraordinary achievement. So whereabouts are you with the mission now? When do your science observations begin?
So we actually currently are commissioning the instruments and calibrating the instruments. We are in the transition phase. 2 months from now, we should be in our science orbit. Once we transition into our science orbit from our capture orbit, we'll start our science phase. And part of the work that the team is doing right now is not just actually commissioning the instruments, but also we're preparing for the maneuvers that we need to do to transition into science. So currently we have 3 planned maneuvers. So we need to design those maneuvers and be preparing for those. And the science basically will start right after we transition into the science phase, but then we will release this first set of data September this year. The data will be released with no restrictions. It will be open to everyone and to be used by everyone.
And you've just released the first picture of the planet as well, from the probe as well. And I think we have that here that we can show. So I wonder if you can talk us through what we're seeing here.
So this is the first picture, the first image received from Hope probe. This picture was taken 28 hours and 38 minutes after successful MOI. It took us a few days to process it because it was the first image. So we were still understanding the image better while it's being around Mars and calibrating the instrument for that. And it was released on the 14th of Feb.
I think you've captured the planet's best side, I have to say. I mean, you've got the Tharsis volcanoes there. It's a beautiful shot.
And it was taken at an altitude of 25,000 kilometers. It's actually 24,800 kilometers roughly, so almost 25,000 kilometers. And as you can see, I mean, you can see the ice clouds on the top left of the image, and also on the bottom right side of the image, you can see those ice clouds, which is amazing, which is part of the study that the Martian that our mission is going to be doing. And if you actually zoom into the middle part, you can actually see Olympus Mont at the dawn area, where the sun, like just the beginning of the dawn. And it's amazing that the first image taken by us has like an image of the highest peak in our solar system. And it's at the dawn of that basically planet or that area, which for us as the UAE, it's the dawn of a new era, given the impact that this mission had. And actually, hopefully, like these high resolution images will be available online. So if you actually zoom in to the higher part or the upper part of the image, around, let's say, 1 o'clock, you can actually see layers of clouds and the atmosphere, which is amazing. And same thing happens also in the bottom part. And you can see it clearly, like layer of clouds, and something that we didn't expect to see, to be honest. And as you also,
this goes right to the heart of the science that the mission is going to perform, isn't it? The atmosphere. Yes. Tell us a little bit about that.
So we'll be studying the Martian atmosphere, basically the relationship between the lower layer and the upper layer of the Martian atmosphere, and the escape rate of hydrogen and oxygen, if I just speak about it in general. But then basically the scientific community around the world, for the first time, they'll get a holistic view of the Martian atmosphere at different times of the day, at different seasons. That's what makes Emirates Mars mission unique. And this is what makes the set of data that we'll be sharing with the rest of the world unique also. And we hope that this is basically, because a lot of the studies that happened in the past were based on data collected at a specific time, at a specific season, and then some models were developed around that to simulate the actual atmosphere or the characteristics of the atmosphere. And now the scientists will have the actual data to use. And and this is the main side. And these questions that we came up with and these investigations that we have are basically based on the MEPAC recommendations. So it's not something that we came up with. It's actually something that resulted from previous missions investigating Mars's atmosphere, and based on that, we came up with these questions that we hope future missions that will be going to Mars will be based on the data that our mission will be providing.
One of the things that excites me the most is that the exploration of Mars is turning into this global endeavor with people slotting in and trying to advance the science in this way. And the other thing that you mentioned was that we saw dawn, of course, over Olympus Mons in that image, and this mission represents this new era and a dawn for the UAE. Tell me a little bit about that and what the deeper motivation for moving into space exploration is.
So what's unique about Emirates Mars mission compared to other missions is that it was not just driven by science. Science played a big role. But the set of requirements that we received from the government when this mission was first was assigned to us and before its announcement is that there are a bunch of strategic goals that are basically the government would like to achieve. However, and using this Mars mission and UAE space program as a mean or a tool to do that. So the number one priority that the government put for us is basically reaching Mars before the 2nd of December 2021. And the main reason behind that was to inspire Emirati youth to go into STEM. So a young nation like us is able to reach Mars in less than 50 years, then we can do much more. And that STEM and technology is the future, and it's a priority area for us as a country. Why is it a priority area for us as a country? Because UAE government believes that to be able to have a sustainable development, we need to have a creative and innovative knowledge-based economy, but on top of that, a competitive knowledge-based economy. So it's about the future of our economy. And to be able to actually have that, we need to have a strong science base in the UAE to support that effort. On top of that, we have critical national challenges, which includes basically things that are linked to the environment. Let's be very honest, we live in a very harsh area in our planet. So water resources and food resources are challenges for us, big national challenges. So we need to have our scientists and engineers to find solutions for that. But again, obviously we won't be able to do that through one Mars mission, but it's about getting that set of skill and creating that R&D culture we need to have in the UAE, and also to create that ecosystem that will support the establishment of an advanced science technology sector. So it's a catalyst for a change, a disruptive change in the UAE. The government wanted to see a big shift in the academic sector and the industrial sector, in the ecosystem for the economy and the sector supporting the economy. So it looked at Mars. So the first set of requirements we received was actually, so as I mentioned, the 2nd of December being 2021 being the deadline, and on top of that, the very strict budget that we had to stick with. And on top of that, going to Mars for the first time. So the thing is also that we received from the Prime Minister, he was very clear with us since day one. He's like, build it, don't buy it. You need to learn from others, go through knowledge transfer programs, don't start from scratch, learn from others. It's okay to learn from others. And the science has to be novel. It shouldn't be something that's been done before. We need to give back to humanity, and also to create that culture of giving back through knowledge, and actually the purity of having the science work that serves the bigger picture. So these were the requirements and the story behind the Emirates Mars mission. And
you've also got some really exciting plans going forward, because it's not just about this one mission, is it? There's a whole program of Mars exploration and development that you're planning, including, I believe, you're thinking about lunar landers for the moon, and also a Mars analog base in the Dubai desert.
So these are ongoing projects, yes, and it's been announced. So when it comes to the lunar mission, it's the hope is to be able to land a rover on the moon by 2024, and it's a work in progress. And the analog also mission, it's something part of our Mars 21-17 strategy. It's basically that strategy that's around basically UAE contributing to putting the first human on Mars one day. And whether it doesn't matter what's the nationality of that person, as long as that person is the citizen of planet Earth, that's what matters. So, but the UAE wants to play a role in that, and big part of that is because if you're able to put a human on Mars and make him have or able to live on that planet in a sustainable way in such a harsh environment, then a lot of those solutions that are developed for that could be used here on Earth. So this is the merit or the vision for that project, and that's why and the analog project is part of that bigger program.
It's absolutely fascinating. Now we've got one or two questions that have come in. For example, where on Earth is your deep space network, as it were? Where do you get your communications from?
So this is one of the reasons why we're able to actually deliver the mission on time, and also with the budget. So we had only 6 years to deliver the mission, which is quite tight, with a very tight budget. It's because we didn't start from scratch. We started where others ended. So instead of building facilities on our own and doing everything on our own, we decided to be effective and efficient. So for example, we have our clean rooms and our labs in Dubai that we use for testing the spacecraft, but we don't have the full environmental testing equipment. What we did is we rented facilities. And one of the facilities that we use, for example, in Colorado, in Boulder Aerospace, and also at the University of Colorado at Boulder, they had also facilities that we use for our environmental testing and also our integration activities. And for example, when it comes to the Deep Space Network, instead of building a network around the world, we decided to utilize that, and basically we are utilizing the DSN network and signed a contract with the DSN network to be able to use them to communicate with our spacecraft. But then the command and control center is in the UAE, so it's linked to the Deep Space Network around the world, and we're using that to communicate with our spacecraft. So it's about that model of collaborating rather than going into a race or challenging each other. So working as one community, as a space science community, or as a deep space explorers community, and utilizing what exists. Usually nations take different approaches of doing everything from A to Z on their own. We decided not to take that approach.
Understand. So Omran, thank you so much once again for joining us this evening. If you can, stay around because we're going to have more questions coming your way. So yeah, thank you so much and congratulations once again. And now it's over to Lucy.
Great, thank you, Stuart. It's so fascinating, beautiful image of Mars to see it in the totality like that. And I'm just going to check the time. We are just over an hour away from hopefully a successful landing on the surface of Mars. But we're going to go now to Dr. Michelle Minetti, who is a co-eye on the SHERLOC instrument on the Perseverance rover. And she's a Mars 2020 long-term planner. She's a member of the Mars Science Laboratory science team, which landed the Curiosity rover on Mars. So she has a long-term and sort of deep experience of operating rovers on Mars. Her research, though, looks at laboratory experiments where she's trying to recreate rocks that are detected by those rovers. And she's investigating connections between Martian meteorites, actually, and the rocks then studied directly on the surface of Mars. Now, we don't have Michelle with us this evening, but Stuart caught up with her earlier on to talk to her about her perspective on the Perseverance rover.
Okay, so Michelle, thank you so much for answering our questions, joining us here. It must be pretty exciting at the moment. Tell me a little bit about how you're feeling. What's the balance between excitement and terror?
It's just like this intense emotion that is kind of inside you the whole time, where it's hard to focus and you're excited, but you're nervous. So it's a whole mix of emotions that, and ultimately, you're excited for what's going to happen because where are we going to land? What's it going to look like? You're nervous because it's so complicated and you're hoping that everything goes smoothly, but it's in the hands of the spacecraft. It got its commands to do its entry, descent, and landing sequence last Friday. So It's totally out of your control at the same time.
And it surprised me just how long ago Curiosity was. I mean, is it 2012? I mean, that's wow, time has absolutely flown by.
Yeah, we just passed Sol 3000 on Curiosity, so it was a very big event, and that it's hard to understand what that means, but the passage of time for me is very well exhibited by my kids' ages when it landed, when Curiosity landed. My eldest was in 3rd grade, and now she's a sophomore in high school.
Now, the two missions, Curiosity and Perseverance, they have quite different flavors of some of the science investigations that are going on. Tell me a little bit about where Perseverance is pushing, and then we'll chat about SHERLOC, your instrument, which I'm fascinated about.
Oh yeah, so Curiosity's goal was really in the March of Mars exploration was trying to understand and find habitable environments, understanding that was Gale Crater a habitable environment, or what kind of habitable environments it hosted in the past. So the instrument suite was really dedicated to looking for that. We have instruments to study mineralogy because that tells you something about habitability, organic chemistry and volatiles with the SAM instrument. So those instruments are really aimed at that. Whereas Perseverance, while outwardly Curiosity and Perseverance look the same, the instrument suites are totally different. The guts of the rovers are completely different because where Kemen and SAM are on Curiosity, the whole system that we need to collect the samples that we hope one day will come back to Earth is inside of Perseverance. All the tubes and all the processing of those sample tubes after we drill them and bring them into the rover are there. So the instruments out on the end of the arm, like Pixel, which looks for elemental chemistry, and SHERLOC, which looks for organics and minerals, are going to look at those rocks in as fine a detail as we ever have before on Earth, to be able to look for the mineralogical and the textural and the bio and the organic signatures that would indicate to us that those rocks are really worth collecting.
And this, I think, is one of the most fascinating aspects about Perseverance at the moment, is this looking for potential biosignatures and really having a sort of a strong focus on not just looking at whether Mars was habitable in the past, but whether it may even have been inhabited. So I'd love you to tell me a little bit about how you go about that investigation. What is it that you're looking for that would make you think that there was once life on Mars?
Well, it starts with the landing site that we selected. So Jezero crater is a much older crater than Gale crater. So we're looking at a much deeper time on Mars than we were previously. And that's important because we know that life developed early on Earth. And we know that conditions were more, we think conditions were more favorable earlier in Mars's geologic history. So it makes sense to keep pushing that window back to look for it. But Jezero is also, like Gale, was once a lake. It has an inlet channel, it has an outlet channel, and it has a beautifully preserved delta, which on Earth, you know, those are the places where we go drill for oil. They have, the sediments are very fine. They trap organics, they trap hydrocarbons. Of course, a lot of that has to do with how much biomass is on Earth, but in that environment, we know that's a place where you can trap organics and preserve them over geologic time. So the first step is just that we're going to a place that we think has a high likelihood of having been habitable, and then also having that chance to preserve those signatures. So when we're on the ground, when we're focused on that particular goal, we're going to be looking for those kind of fine-grained rocks, the kind of mudstones that you would expect those organics to be in. We look for particular textures and structures. I know in some of the press conferences earlier this week, they were showing pictures of stromatolites, which are ancient structures that are indicative of life that we find on Earth. It's finely interbedded sediment, like silt grains, mud grains, and then organic material, bacteria that live in between the layers. So if we found a structure like that, we'd be like, oh, let's go look at that. So we're looking for those kind of structures, and that SHERLOC has the ability to look for those organics in their spatial context. So it matters. Sam on Curiosity has found organics. Almost every hole that we have drilled in Gale Crater has turned up organics, but the sample is just all a jumbled thing of rock, right? That's just how we collect samples there. This is where we can look at those organics in place, how they are related to the minerals, how they are related to the structures in the rock. And that really tells a much richer story about how those organics got there, leading you farther down the path to being able to hypothesize with more confidence that this was life.
Yes, the SHERLOC instrument itself, which is a great name, it's only beaten by the fact that you've also got a camera called Watson. So tell me, how do those two work together?
They work together very much like Benedict Cumberbatch and Martin Freeman do on the show. One is the brilliant and observant main character, SHERLOC, looking for those organics, looking for those minerals, digging into the details, and Watson, the ever steady sidekick, providing the context for all of those beautifully fine, detailed observations that SHERLOC makes. But also very flexible, very adaptable. Not only can Watson focus it on rocks and look at them at very fine scales to support SHERLOC, but Watson is a cut to print version of the Molly camera on Curiosity. So if we get a selfie from Mars 2020, it will be from Watson. So Watson can look from grain scale to landscape scale, a nice flexible sidekick for our star SHERLOC.
Yeah, for sure. And I think another really fascinating aspect of SHERLOC as well is, do you have a piece of Martian meteorite that you're kind of like taking it home? And tell me what you're going to use that to tell you.
So yeah, it's a piece of meteorite from Carolyn Smith at the British Museum, and it's a way that we can test the performance of the instruments, not only Watson but SHERLOC, with a sample that is known. And it's obviously very comparable to the kind of rocks that are going to be on Mars. So it provides a nice fixed standard by which we can take, like versus like, right? It's really an apples to apples comparison. How is my instrument behaving looking at the rocks in front of me? How is my instrument behaving when I have a known Martian sample sitting on my rover? So it's a nice check, and plus it is fun to think that you're saying, did you lose this?
So we're just about coming to the end of our time, but briefly, I also wanted to just ask you about how you plan a mission like this. You're part of the long-term planning team, and what kind of planning can you do before you actually get down on the surface and really sort of see where you are and what you might want to do?
We started years ago. As soon as we knew that Jezero was the landing site, we have beautiful images from all the orbital assets that have been around Mars for decades. So we use those images to just look at the geology. What can you learn? What do you think you can hypothesize from those images, the structures, how they're related to one another? And then we spent a lot of time just practicing path planning. If you landed here, where would you go? How would you prioritize which places you stop? What samples would you collect there? So by practicing that, obviously, we don't know exactly where we're going to land, but by practicing that, you get a chance to practice your ability to prioritize, your ability to think about how to change the order of what you're doing and the priority of what you're doing to be able to make sure that you maximize the amount of time on the surface. So we've done a lot of that, and it will be very exciting to see where we actually land, so we know whose practice was closest.
Well, we have all our fingers crossed. We're cheering you on. We just, can't wait, to see what the science is going to come out of this. So, Michelle, thank you so much. It's been a real pleasure.
All right, thank you so much. We appreciate it. Go
Thanks.
Perseverance.
Go Perseverance. I love that. That's definitely what we're all thinking this evening. Fantastic. So I think now we are able to move on to our next speaker, who is Professor Sanjeev Gupta from Imperial College London. So Stuart, you'll know this. Sanjeev is a geologist by training who worked on, amongst many things, rocks laid down under the English Channel. And so he made that interesting transition, moving from rocks under the water on Earth to studying floodplains on Mars. And Sanjeev has extensive experience working on Mars rover missions as well. So he is a co-investigator on the Martian camera on the Curiosity rover, co-investigator on PanCam, which is of course close to our hearts because that's on the European Space Agency rover to Mars, hopefully going next year now, and is a collaborator on the Marscam Z camera team on Perseverance. And he can only be with us at the beginning of this evening because you have to leave early, don't you, Sanjeev, for a meeting because of Perseverance landing. So we're really grateful that you can give up some time this evening for us. And I think if I'm correct, you have some slides that you want to talk us through. So
yeah, I can. Can you hear me?
I can hear you.
Yeah, that's great. Well, it was amazing to see Michelle there. Michelle is one of my closest friends on MSL and Perseverance, and we're both part of the long-term planning group. So she said lots of things. That's great. So let me just show, I think if my slides can be shared, I can just run through those. And okay, so I think Michelle's talked a little bit about this, but this is a mission that's not only about finding life on Mars, and that's the title and that's the big picture view, but also as a geologist and as a planetary scientist, it's really about the early evolution of Mars. It's about planetary evolution. What can we learn about Mars's early history, geological history, and what does that tell us about Earth's geological history? Because actually, because Earth has this plate tectonic cycle, all the oldest rocks on Earth, well, many of them are not preserved. Those that are preserved are heavily deformed and they're very, very difficult to read. And so actually, whenever you get a story about the oldest life on Earth, it's always kind of controversial. There was a story a few years ago about some possible early life on Earth from Greenland, but then people came along and said, oh, no, these are deformational structures. But the beauty of Mars is because Mars hasn't had large-scale tectonics, it's not had plate tectonics, we have some of the oldest rocks still preserved on the surface, and large parts of the surface of Mars are covered in very, very ancient rocks, older than 3.7 billion years. So in some ways, looking at those rocks, bringing them back to Earth, will not only tell us about the early evolution of Mars, but maybe tell us something about our own early evolution. So if you go to the next slide. Okay, so this is one of the beautiful images from Curiosity, from Glen Torridon, where we are at the moment. And what you see today on Mars is this desolate, dry planet. So in the foreground, you can see these light-toned rocks. I mean, it looks absolutely desolate. But actually, those rocks in the foreground, if you look at them closely, using what Michelle was talking about, the Marley camera, what is the Watson camera on Perseverance, we can see that you can't actually see grains. The makeup of those rocks, the grains that make up the rocks, are actually finer than 60 microns. And we call these rocks mud rocks, basically mudstones. And these are mudstones, but when we look at them in detail with both the Marley camera and the Marscam camera, we see that these rocks are beautifully laminated. That means that they have layers that are less than a millimeter thick. They're about a millimeter thick. And they're pervasively layered. And we've now driven through almost 200 to 300 meters thickness of these rocks. And the best way to interpret these rocks is that they're ancient lake deposits. We can't form these sorts of rocks in air because we need some form of grain size segregation to produce that layering. So we see these beautiful layered rocks, which are ancient mudstones. And basically, this landscape that you see before us would have been an ancient lake on Mars 3.5 billion years ago. So a little bit younger than where Perseverance is going. And these lakes would have existed for hundreds of thousands, if not billions of years. Okay, if we go to the next slide. Okay, so this is perhaps one of my favorite newspaper headlines of all time. This is from the New York Times magazine section in 2011, I believe, at the phase of that Mars mania. And, you know, when Percival Lowell was active in observing Mars with his telescope, with a direct line to the New York Times press office, basically. And we see this amazing headline of Martians build 2 immense canals in 2 years. And at that time, people genuinely believed there was an intelligent civilization living on Mars. And I'm sure many of you know this story. And there's been a wonderful book recently out by a Cambridge historian about this, about how these linear features that were observed on telescopic images of Mars were misinterpreted as canals and built by an advanced civilization. An amazing story developed out of that. Well, obviously that was shown not to be true, and Mars was then actually shown to be a dry, by the time that Mariner missions went, a dry, dusty, desolate place. So you go to the next slide. So modern Mars is dry and dusty without water, but Mars 3.6, 3.7 billion years ago was a watery abode. There's plentiful geomorphic evidence, geological evidence for rivers, both erosional rivers, so valleys, but also depositional rivers, the traces of rivers that built up sediment records. There are lakes filling craters, and there's potential evidence, it's highly disputed, of a possible northern ocean in the northern lowlands of Mars.
Okay,
fantastic. And this is a huge debate on ancient Mars between the geoscientists, the geologists, and the climate scientists, the climate modelers, because climate modelers struggle to make Mars warm and wet early in its history. And this is not a solution that's been resolved at the moment. It may be that Mars was not, you know, hugely wet, but maybe sporadically wet. So how it's not clear how long those wet durations lasted, whether they were intermittent or whether they were long lasting. And these are questions that we need to resolve if we're going to search for life, basically. Next slide, please. And next. So the mission objectives are firstly geological exploration. So the aim of the mission is to explore an ancient environment on Mars and reconstruct that environment and understand the process of formation and alteration. So this is partly aimed at getting context for our search for life, but also intrinsically, we want to understand the geological evolution of Mars. And, you know, it may be actually that life never existed on Mars, or that we don't find it, but we have to keep searching. And so the one tangible gain we get is that we always learn more about the geology. We reconstruct and we progressively build a picture of Mars originally being a Lego planet, you know, like a Lego model, to now a really refined understanding. It's almost like, geologically, we're almost like 200 years compared to Earth. You know, we have a really rich understanding of Earth now. We have chronology, we have timing, etc. We don't have this for Mars, and we're sort of starting afresh with a new planet. And so one of the big important questions that people have, and one of the important aims of the mission in terms of sample collection I'll come to, is we don't have a precise chronology for Mars. The chronology we have has been reconstructed by crater counting and comparison with crater count surfaces that have been dated on the moon with samples, and comparing the crater counts there and doing some physics associated with that and transferring that knowledge to Mars. But what geologists and planetary scientists really want is precise chronology, timing for rock units on Mars. Next slide, please. And then obviously the big picture, you know, what probably missions get funded for is habitability and biosignatures. So habitability is about whether there were right conditions for life. So, you know, we have a hypothesis that Jezero was an ancient lake basin with a delta in it, but that's from orbit, and it's really not until we get on the ground that we absolutely know. And, you know, have a really great story from Curiosity. Very early in the mission, we came across these pebble beds. And it's kind of a common occurrence on Earth, finding pebble beds. You know, you have some around where I live in near Greenwich, basically, from the ancient Thames River, you know, small centimeter scale rounded pebbles. We came across this and kind of initially didn't think much of it. It's like, oh my God, we've got rounded pebbles. And it was like, those rounded pebbles, which were a centimeter in diameter to up to 4 centimeters diameter. You can't move those pebbles and you can't round them by wind action. They're too big to move by wind. So basically wind action can kind of move grains creeping along the surface of about 2 millimeters diameter, not 1 centimeter, certainly not 4 centimeters. And so actually that was, whilst, we've had this funny story about NASA discovering water on Mars again and again and again. This was the first sort of in situ evidence for the flow of liquid water and sustained liquid water flow on the surface of Mars. So really confirming the observations from orbit. And that's what scientists do, they fine tune the hypotheses. And so with habitability, we want to fine tune our hypotheses for Jezero crater. And whilst we see a delta and there's evidence that there was once a lake, what I want to really see is, I want to see lake sediments like we've seen in Gale crater and like we find on Earth. So we have fantastic exposures of lake sediments in Britain, for example. If you go up to northeast Scotland, you have them in what are called the Caithness flags, which are Devonian age, beautiful laminated mudstones. And also if you go to the Northwest Highlands, we have this fantastic succession called the Torridonian succession that's about 1 billion years old. And we have beautiful laminated sediments. And we've been using those as analogues to help us identify Martian lake sediments. And then obviously, in terms of life, we're interested in biosignatures. So we're assessing the habitability, but we're seeking evidence for past life. And obviously we'd love to find what you can see in that image, which are stromatolites, which are microbial mats that formed on the seabed or the lake bed and form these dome-shaped structures. And they're macroscopic features. So, we're kind of like excited about Mars-Chem Z being able to image one of those. But I suspect it's more likely that the samples we collect and bring back to Earth, it's what those we will be looking for signatures of life in. Next slide, please. And then the big goal really of the mission is preparing a returnable cache. So what the mission is going to be doing, and I'm sure Michelle talked about this, is selecting samples, drilling samples that are stored in tubes and on the rover, and that will be depotted for future return. And the idea is that we have at least 2 depots, one in Jezero crater, because obviously the issue is you can keep putting tubes onto Perseverance, but should Perseverance fail at some stage, we won't be able to get those tubes out. So we want to be able to leave a depot for safety's sake, having collected enough samples that we think they're returnable, because you want to have enough diverse samples that governments and the public are prepared to spend the money to bring them back, because that will be extremely expensive, obviously. So the idea is that we would leave 20 in Jezero just before we leave Jezero, and we would collect some doubles, basically. So some of the highest priority samples would actually be carried on board Perseverance out of Jezero. And then after the prime mission, we will actually drive out of Jezero crater and go and explore this other area outside Jezero, which has this amazing, really ancient terrain. And I'll come back to that in a minute. And so what we want to capture with this sample cache is geological diversity. It's not just about life. It's about, what we're hoping to find, for example, are igneous rocks. So basalts, for example. And one idea is that floor of Jezero crater is actually an ancient basalt lava flow. And that's something we could date on Earth using radiometric dating. So we'd be really excited about that. We'd hopefully sample. So I'll actually come to that shortly. Next slide, please. And we'd prepare for human exploration. We have some instruments to do that. Okay, next slide, please. I should move on. So sort of fossils, we're not going to find leaves or fossil fish, but we're looking for microbial signatures, these stromatolite features. Next slide, please. And here we see perseverance with all the instruments. Michelle has talked about SHERLOC. I'm on the Mars-CAM-Z team with these fantastic geology cameras, and we have a subsurface radar and SuperCam also. Next slide, please. And here we just see some of the instruments. So this is the Mars-CAM-Z cameras, zoomable cameras. They're multispectral, where we can use them to detect minerals from a distance, remote sensing of minerals in the Martian rocks. Next slide, please. Here's SuperCam, so a next generation of the instrument that's on ChemCam, that's on MSL. But this can also do it does laser spectroscopy, but it can also do Raman, so look for organics. Next slide, please. And this is SHERLOC and Watson, and Michelle has already talked about that. Next slide, please. And then what's really amazing is at the end of the arm, we have this turret with this amazing drilling system, completely new, that will drill into the Martian rocks, get a core of sample, and then store them safely. And that's just an incredible new system that's been developed to do that in a safe way. Next slide, please. So you can see here the turret with the stabilizers, and you can see on the side the coring bits. We've got a regolith bit to collect a bit of regolith, and the brush basically to remove dust, so we can use the contact instruments without the dust cover. Next slide, please. And then within that, we've got this whole adaptive caching facility, so we can store the tubes and selectively store them in this system. And then when we want to depot them on the surface, we're not going to leave a whole group of tubes. We're going to actually deposit them individually on the surface of Mars, where they can be collected individually, because the trouble obviously with a set of samples in a system is that could fail basically. So, you know, with individual tubes that are in these titanium tubes that are well sealed, they have better chance that we can, at least if there's some sort of failure, we can recover some of them at least. Next slide, please. So Jezero crater, it lies at the edge of this huge impact basin that formed 3.9 billion years ago, the Isidis impact basin. And it's a much smaller crater at the edge of that. And then outside this, we've got this major area of Nili Fossae, which is this very ancient terrain on Mars. Next slide, please. And so here you can see Jezero crater, and Michelle talked about this. We think it was a lake because you see on the left-hand side, you see a river valley entering the crater, but then on the other side, on the eastern side, you see a valley exiting the crater, going out. So at some point, the lake waters overspilled, probably in some sort of flood flow, and carved that valley that's going out. But that tells us that it's likely held a lake. And then at the western edge of the crater, where the inlet channel is coming in, we see this fan-shaped deposit, which we think is a delta system. Next slide, please. So you can see this here in this map. You can see the delta, and on the crater floor, in the sort of reddish colored stuff, is this very dark toned crater retaining material, which some people think might be an ancient lava flow. And, you know, we're excited to sample that, obviously, and we're likely to be landing on that very, very shortly. Next slide, please. So river deltas are fantastic environments for looking for life. They're habitable environments on Earth, and they bring nutrients to the lake. So this is why deltas are go-to places for astrobiology. Next slide, please. And so there's the landing site. Next slide, please. And, you know, this is going to be happening very, very shortly, so I don't need to talk about this. You're going to hear all about this in a few minutes. Next slide, please. And yes, I don't need to say any more on that. Next slide, please. So after we land, as Michelle talked about, we'll be doing this, planning a traverse to drive through the best deposits that we can sample in Jezero crater, and then exit the crater to go after the prime mission outside Jezero and sample the outside Jezero area. Next slide, please. And we'll be collecting a diverse set of samples. So this is a potential cache from Jezero with the mafic floor unit, the potential basalt, and different other units And what's important is we get a diversity of samples. Next slide, please. And then we would go outside Jezero to this extraordinary layer, a very complex geological map here, but we have these very, very ancient basement rocks, and we'll learn about a much older part of Mars than Jezero, something that we've not visited or sampled before. So that's going to be really exciting. Next slide, please. And these are the sample tubes, etc. And I'm actually going to stop there because it's very close to landing time. So yeah.
Right. Thank you very much. That was a fantastic overview of the mission. We've got lots of questions, but I know we're tight on time, so I think I'll just ask you a couple. So Peter Holmes has asked, will we only know the true nature of Mars, particularly concerning the question of life, by sending human expeditions there? So I think that's a nice question to ask a geologist.
Yeah, I think, well, we'll learn huge amounts from the samples, and who knows what we will find in those samples. And actually, if we do find evidence for life, I think we'll just send human missions because we'll want to know more. We won't be satisfied with just having found life. We will want to know more. And I'm sure there'll be questions about that. Every paper that gets published on the earliest life on Earth, people have questions about it. Scientists always poke holes in that. So I think we will go to Mars. So that will happen.
Brilliant. And one quick question. I'm not sure whether you did mention this in your talk or not, but were you involved in selecting the landing site as Jezero Crater?
So I was involved in the process. I'd actually proposed another site and mine wasn't selected. But what I did do at the final landing site was that I presented the landing site on behalf of the team. So there were individual proponents of the landing site, but also the team did their own exercise. And we gave this sort of balanced view. And I together with one of my colleagues, Bryony Horgan, gave the balanced view about the pros and cons of the site, basically.
Brilliant. Well, look, Sanjeev, thank you so much for joining us tonight. I know you have actual work to do now, so thank you for joining us. Fingers crossed for the rest of the evening, and I'm sure we'll catch up with you at a future AstroFest to hear
thank you very much.
How everything went. Take care.
Okay.
Bye.
We are just 15 minutes away or so from when Perseverance hits the top of the Martian atmosphere, so that's a perfect time to talk to our next speaker.
Brilliant, excellent. So we're going to be moving on to Professor Lucy Berthoud, who is, as I was saying earlier, a Professor of Space Engineering at the University of Bristol. So welcome, Lucy. It's great to have you on the broadcast this evening. Lucy has worked for both ESA and NASA, and her research interests are in microsatellites, interplanetary spacecraft design, and Mars sample return. Perfectly timed to come up with that. So I think, given the time, I'll move on to you, Lucy. So we're really looking forward to hearing what you have to say, and then we'll come to questions answered. So Lucy, it's over to you.
Fantastic. Thank you so much, Lucy. Lots of Lucys. Can't have too many Lucys. Thank you so much for letting me speak to you today about one of my favourite subjects, which is Mars sample return. So what is Mars sample return? Well, simply put, it's when we go to Mars, collect some rocks or dust, and then bring them back to Earth, or send them back to Earth. So let me just show you what I'm going to speak to you about. And that is why return the samples. Previous sample return missions. So there's a lot we can learn from our space missions that we've done in the past. The actual sequence, because it's quite a complex sequence we have to go through to do Mars sample return. And then some equipment that I have, my company, which I work for, Thales Alenia Space, has been building in aid of this mission. So let's have a start and first look at why return samples. Now, Sanjeev has touched on this in his talk. I think there's three main reasons, and this is an engineer speaking first of all, and that is because it is the next step in the exploration of Mars. So we tend to go through a bit of a pattern when we're planning Mars missions, when we're planning a mission to another celestial body. We like to start with the flyby. That's relatively straightforward. Then we go to an orbiter because that's a little bit more complex. You have to do an insertion maneuver to get it around the body. And then you go to a lander, then a rover, then sample return, and then ideally you go to human missions or crewed missions. So that's the first reason, really. The second reason then is really that we can only fit a certain amount of instruments on a rover because the rover's weight constrained. So what we want to do is really bring back some samples like these. These are the Apollo lunar samples with some colleagues of mine, and this is where they're housed at NASA Johnson Space Center, where I actually spent a year working in the lunar sample facility. And so what we really want to do is bring some rocks back to Earth, where we've got many types of powerful scanning microscopes, chemical analysis, and so on, to do some more advanced science. So then the third reason, and this one Sanjeev touched upon, is that it's really interesting to have a look at the surface of Mars, but to be able to bring a really pristine, clean sample back from Mars to Earth, because 3.5 billion years ago, when it's thought that the oldest known life on Earth started, then we can't see that on the Earth's surface, because less than 1% of the Earth's surface is that old, but greater than 50% of Mars's surface is that old. So we've got three really compelling reasons to bring some rocks back from Mars. Now, we have actually got some, as you saw with SHERLOC, we have actually got some rocks on Earth from Mars already. This is actually the Tissint meteorite. And this is a Martian meteorite that landed in Morocco in 2011. It's in the Natural History Museum on display, but it's also been analysed. And how on earth did a rock like this get back to the Earth? Well, it must be that something has impacted Mars. Bits of Mars rock have been ejected off of Mars with sufficient velocity to escape the planet. Then they've found their way through orbital mechanics in through the atmosphere of the Earth, and then they've landed on the Earth. But unfortunately, it's that process of coming through the atmosphere that means that the surface of the meteorite is not pristine anymore. It's not original. And that's why we're particularly keen to get Mars rocks back here on Earth. So what can we learn from previous sample return missions? And I'm aware we're about to, we may be distracted off and go and look at the exciting events at the moment. So please don't worry if I'm suddenly cut off. Yeah, there's been lots of interesting sample return missions. I've mentioned the Apollo missions, which brought hundreds of kilograms of interesting rocks, lunar rocks, back to the Earth. But the Russian lunar missions actually also landed on the moon and brought back some rocks for us through a proper sample return process. Stardust is another sample return mission, which went to the comet Wild. Then OSIRIS-REx went to the asteroid Bennu. Genesis was a sample return mission which went to the solar wind and collected some samples of the solar wind. And you can see that one hit the deck pretty hard in the surface of Utah. That's the returned capsule there, and it hit the deck pretty hard. So the NASA team actually did a fantastic job of recovering that one and practically recovered 100% of the samples. Hayabusa is the Japanese missions to asteroids. Hayabusa 2's just recently returned, and Chang'e 5 is the Chinese mission that went to the moon in December and has also brought some samples back. So we're very, very well set up, if you like, in terms of sample return missions that we can learn from. Now, of course, there have been many past Mars missions that we can learn from, not sample return ones. And this will be the first interplanetary sample return. But you can see here some of the most recent Mars missions, including the ones in pale blue are NASA missions, the ones in orange are non-NASA missions. And on the right-hand side, you can see some of the elements that we'll need for a Mars sample return mission, including a Mars sample return orbiter. So that's the thing that's going to go to Mars and then bring the samples back from Mars. It's like the cruise orbiter. And also we need a Mars ascent vehicle. So that's a rocket that lifts off from the surface of Mars that we can put the samples into. So let's have a look in a little bit more detail at the sequence, because it is a complicated one. And NASA and the European Space Agency, who have been working on this together, have been through many different scenarios to see what's the best way of doing this. But this is what they've come up with. So here you can see Perseverance, and it's left some samples, tubes. This is 2026, so 6 years later. Sample Fetch rover is going to come and load those samples up into a canister. The canister is then launched up. That rendezvous with the Earth return orbiter. The Earth return orbiter mounts it into the Earth entry vehicle, and then the Earth entry vehicle will plunge through the atmosphere of the Earth. Okay. So yes, let's just dive into that in a little bit more depth. You can see here the 3 necessary launches that we have. On the left is the Mars 2020, the Perseverance rover mission that we've watching at the moment. And then in 2026, we have the Earth return orbiter will launch. And that Earth return orbiter will go into do the long cruise phase to Mars, then we'll just hang around patiently waiting in Mars orbit for the orbiting sample container. Now, the next one is a really crucial one, and that is the sample retrieval lander mission. And that launches that sample retrieval lander and the sample fetch rover, which both come together. And the sample fetch rover goes and grabs the tubes, puts them in an orbiting sample container, which is loaded into the rocket. The rocket delivers the orbiting sample, which rendezvous in orbit with the Earth return orbiter. And then the Earth return orbiter, it sort of encloses the samples in a biocontainer. The biocontainer then is slotted into the Earth entry vehicle. It's a bit like a Russian doll sequence, if you like, everything inside, everything else. And then that Earth entry vehicle comes through the atmosphere. And once it hits the deck in the Utah desert, then it'll be recovered off to the Mars sample receiving facility. So after that, let's have a look at the schedule if we have time. And the schedule here for the whole Mars sample return mission, you can see at the top there. In 2026 is when those 2 missions will launch. Then at the top, the Earth return orbiter, you can see will wait patiently. And what we're trying to avoid there, I don't know if you can see there, is we're trying to avoid having anything, doing any complex emissions on the surface during the northern winter, but also during the global dust seasons. Those are the brown bits at the top there, and also during the regional dust storm seasons. So we're trying to avoid those. That gives us a little window of 13 months, you can see there, which is when we can do our surface activities. Once that's done, and you can see all the different sorts of activities that will take place during that time, then the Mars ascent vehicle, that rocket, takes off, rendezvous, there's the spiral up, and then the spiral up is because there's electric propulsion that's going to be used to change the orbit, and then there's a long cruise back to Earth, and then landing in 2031. So I noticed there was a really good question about why are the sample return samples only just coming back in 2031? Well, hopefully that's answered that one. So just lastly then, for the sample return equipment, and this is covers the various different equipments that we're looking at here in Europe. And the European Space Agency has negotiated with NASA for some of the parts of this mission. And the first part that they've negotiated is the Earth Return Orbiter. So this really crucial part is going to be built by Thales Alenia Space, the company I work for, Airbus, and many other space companies across Europe, all working together. It's a really interesting challenge, and they've already been working on it for a few years already. The next part is the sample fetch rover. That's also being built by across Europe by all these different companies. And you can see here, it's a slightly simpler, more modest rover, but has an interesting task, which is to collect up these cached, is it cached or cached, sample tubes. I think there's 43 of them, which have been taken on Perseverance and which we're very excited to recuperate here on Earth. So one of the next things, so I've got an image here which is of the Thales Alenia Space rover assembly line. So once we get the samples back to Earth, then we're going to need to investigate and house them in a special facility. And it may look a little bit like this. So this was actually a rover assembly line. So it's got these ultra clean multi-chamber isolators with glove boxes. But for building a rover, you only need to worry about contaminating Mars. I say only, but already that's a really expensive and extremely challenging task. But this time we need to worry also, because there is a slight possibility of life, the potential for life on the Mars samples, we have to worry about protecting the Earth landing site. And as of course the sample itself. So what we use is a positive and negative pressure regime. You may have come across this concept at the moment in the COVID-19 pandemic. This is being used in hospitals, pressure regimes to stop the virus spreading around the hospital. So we're going to use the same concept, but we don't just have to do it one way, we have to do it two ways. So we need to build a box within a box, and this is called a double-walled isolator.
Sorry to interrupt you, Lucy. That was fantastic, but I think we're going to move on to listen to mission control now, because we don't want to miss this key separation point. So you're going to be with us, and we will then come back to you afterwards. But I think we're going to hand over to Stephen Clark now from Spaceflight Now, who's able to give us the feed from mission control and the latest update. So hopefully, Stephen, you're there.
Yes, the Perseverance rover is about to enter the Martian atmosphere at about 12,000 miles per hour. And this begins the 7 minutes of terror that you may have heard a lot of reference to over the past few minutes and hours and days. And this is a key moment. And we just heard confirmation of entry interface. So the heat shield is now going to build up to about 2,400 degrees Fahrenheit, around 1,300 Celsius over the next few minutes to as the spacecraft decelerates and takes aim on Jezero crater.
Doppler indicates entry into the atmosphere. Bank 1 completed. Doppler indicate reversal, bank reversal.
Max decel 10 Gs.
Bank 2 start. Doppler indicate reversal. Bank 2 complete. Doppler indicate reversal.
End of range control, range minus 1.9 kilometers, cross range minus 2.4 kilometers.
So one of the next steps will be the deployment of the supersonic parachute. It's one of the key moments during the entry. This parachute's about 21 meters wide, 70 feet in diameter, and it's going to deploy at a speed of Mach 2.
Software start.
UBMD jettison.
Doppler indicate chute deploy. Heat shield set. Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers. LVS valid. Priming. TBA is nominal. Back shell set.
SDS level?
Constant velocity
104.
accordion. Constant velocity accordion, altitude error.
Throttle down.
Tango Delta. Nominal.
Bring me stable.
Well, in case you didn't get it from the body language, looks like everything is nominal. So it looks like Perseverance is in Jezero crater at the start of a new adventure in the exploration of Mars. NASA is 2 for 2 with its sky crane. In case you didn't quite catch what was going on there, the Martian atmosphere is quite tenuous, and so you need the heat shield, the parachute, and then some sort of retro rocket assembly to slow you all the way down and put you on the surface of Mars. Twice NASA have done this with this amazing contraption, the sky crane, that lowers the rover to the ground, and twice it appears they have had complete success. Lucy, are you still with us? What's your feelings at the moment to see that?
I am absolutely overjoyed. Absolutely, I am dancing around my chair. I'm like, woo!
OL3, I have what I need.
I mean, it's quite astonishing that sky crane system had, I mean, hardly ever, you can't really test it in Earth gravity. So the test was Curiosity in 2012, and here we are again.
Yes, absolutely. I mean, I think of Perseverance as kind of an upgraded Curiosity. It's like an SUV that you've got an upgrade on. So they did already have a really good experience of it working in 2012, and they had some extra measures added onto this system, which would have made it even more likely that it worked. So, but I am still so relieved and overjoyed.
Yes, indeed. What sort of lessons did they learn from that 2012 landing? Because from the outside looking in, everything looked as if it had gone, kind of perfectly. So what extra steps have they been doing to improve the landing system?
Yeah, so there's two really major things that they've added on, two features, you could say. One is something called relative terrain navigation, and that's where they scan the terrain, compare it to a map, and then work out where they are, so they can.
Lucy, I'm going to interrupt you yet again. I'm so sorry. The first image is just being shown from the rover, and confirming if we needed any more confirmation that there it is on the surface of Mars. I can see that makes you pretty pleased as well.
Yeah, what can you say to a photo from another planet? It's just overwhelming, isn't it?
I know. I wish my internet worked that fast. I mean, that was astonishing how quickly that came back.
Mm. Yeah, absolutely.
The animation that we were seeing earlier, as it was coming through the atmosphere, that's presumably computed in real time from telemetry that's being sent back from the Perseverance spacecraft itself as it's moving through the atmosphere.
Yes, exactly. That's just what's happening, and it was quite interesting. You could see the Mach number, you could see the altitude, and you could see the fuel going down. And I was looking with slight alarm at the rate at which the fuel was going down. But then they actually hit the deck with some fuel to spare, so there was obviously a margin in it.
Fantastic. Now, Lucy, we've interrupted you twice this evening. Would you like to finish your presentation for us?
Yes, absolutely. It was definitely worth it. If we could have the slide somehow. And I'm just getting my clicker back. Yes, so this is the sample fetch rover. So I'm slightly selfishly thrilled as well, because the success of Perseverance, obviously there is many more steps to go for the Perseverance to store the samples within those sample containers, those long tubes. And then there's more missions to go in order for us to be able to pick them up. But the really most challenging part was getting Perseverance on the deck on Mars. So I can't tell you how thrilled I am about that. So yeah, this is the slightly simpler version, the I won't say the poor cousin, but the younger brother of Perseverance, which is the sample fetch rover, which will be going to pick up the sample tubes in 6 years' time. And yes, I think I showed you this. This was the rover assembly line. And what we were doing, yes, I was explaining about the positive and negative pressure regime, excuse me. And that's what we use to build our what's called a double-walled isolator. So this is going to house a Mars sample when we get it back on Earth. And we've built a prototype with the University of Leicester. So this is a picture of the prototype, and this is the first double-walled isolator in the world. And it may look like a large oven, but it's actually a sealed box within a box where we can keep the Martian sample on Earth safely. We can connect this box up to our powerful microscopes, and so on. But if you've got a box within a box and you've got your precious Mars sample inside, how do you manipulate the samples? Well, we're going to have to put some robots in the box with these samples. And then, so let me actually firstly show you just, I've just got a few minutes of video. This was on the news, and this is my colleague who's showing somebody around the double-walled isolator. So yeah, these are the kind of robots that we're working to put inside the double-walled isolator. You can see here that what happens is somebody puts on the gloves, they move the gloves, and then the robot shadows the movement. So this is called remote manipulation. And geologists are very fussy. They like to have a really good feel for their samples. So they don't like to have robots doing their stuff. And so they want something called haptics, which is where you get force feedback from the robot. So it means you get a bit of a feel, so you can do that fine motor coordination for manipulating the samples. So yes, I think that's my final slide. I hope you've enjoyed the sort of whistle-stop tour of Mars sample return, looking at why we should do it, previous sample returns, the actual complex sequence, and all the equipment that we're preparing for it. There's so much more exciting work to be done, and the next steps after that are even more exciting as we start to think about building bases on the moon and landing humans on Mars. So thanks very much.
Thanks, Lucy. That's just so fascinating to hear all that, because one of the things that I find that's just astonishing about all of this is that not only is this kind of exploration of such cutting edge science, but the engineering behind it is phenomenal. And everything that you've been describing about preparing the next 10 years for the rovers and the sample fetch rover, bring it all back, the double-walled isolator to keep the samples pristine. I mean, you know, this is science fiction to me. So this is fantastic to hear. Now, stay with us, because Lucy, I think, has got some questions from our audience that she would like to ask you.
I have, yes, thank you. I'm sure you can hear me. So, wow, what a ride. That was absolutely fantastic. And I have to say, I've got my champagne here to start celebrating, but I'll hold off until the end. So amazing, amazing. So congratulations, NASA, and all the teams who've been working on this, including people around the world. So Lucy, we've had lots of questions in for you, but I wanted to start with, if I can just find it, a question from Josh, age 7, who asks, are Perseverance's eyes cameras, and do they see the same things that we do?
Well, what a wonderful question. Yes is a short answer. You could definitely think about the eyes as cameras, and you could also think about the spacecraft having a nose for sniffing and kind of doing chemical analysis, which a lot of our Mars rovers do. And what other analogous things could we find? The arms are the robot arms as well. So yeah, there's a lot of similarity. And I encourage you, Josh, to think about space as a career, as you're already interested. And there's going to be so many jobs for people in this area in the future.
I definitely support that. It's a fantastic, fantastic area to work in. And like we've seen tonight, so many exciting things happening rather frequently now. So Lucy, there's been another kind of series of questions that are around Martian meteorites, and Adam's asked, and Luke has asked, and W. Anderson has asked, how do you know that meteorites actually come from Mars?
Yes, that's a very sensible question. Well, fortunately, sometimes people see them dropping through the sky. So that Tissint meteorite that I showed a picture of that landed in Morocco, people actually watched it land on Earth. So we definitely know that it was a meteorite. And then in terms, so that means, of course, it's come from outer space. Then we've got to narrow it down. How do we know that it's from Mars? And that's done by a combination of factors. You can't just do it from one thing, but one of the things I think I mentioned was we can look inside the meteorite for the gases. So there's certain combinations of gases, and you can do isotopic analysis of some of those gases to see if it's the same combination that we have on Mars. You can do geological analysis of the rocks inside, and so on. So I'm not a meteorite specialist, I'm an engineer, but yes, that is a very good question, and certainly the question I asked of the geologists when we first came across this question.
And another one actually from Greg. So are there any degradations in the conditions of the rock from the time, so when we'll be looking in the future about Mars sample return, are there any degradation conditions from the time of collection to delivery at Earth that might affect the quality of samples that are brought back here?
Yes, again, this is a very interesting question, because when we have been thinking about the design of the mission, we've been very concerned that the rock arrives in as close a sort of state as the original as it has come straight from Mars. So one of the things we considered was, could we keep it the same temperature as it was on Mars? And that was one of the things that was decided, that it's just not possible to keep it the same temperature. It's going to have to go through some fairly high temperature, obviously not the same as coming screaming through the atmosphere of Earth without a heat shield on, but the Earth entry vehicle will have a heat shield, so it will protect the Mars sample return containers from the worst of the friction with the atmosphere and the heat, and it will keep it within a reasonable amount, but that we can't keep it down at the low cold temperatures that it would normally be experiencing on Mars. So that's one of the things that we have had to compromise on. Let me try and think of some more things in terms of degradation. The Mars rocks are pretty tough, it has to be said, so they can survive coming through the atmosphere without even an Earth entry vehicle around them, so we don't need to worry too much. They will be contained in the canisters, of course, and that's particularly important for the cores. So if they do drill some cores and they pull out the core and put it in the sample container, then you're conserving the stratification, the layers of rock in the same order that you got them in. So if they're taken out of the Mars and then put very carefully and in the Perseverance inside the tubes, then they will be able to conserve that as well, and that's really important too.
Great, thank you. And maybe a kind of related question, because I was watching another one of the videos that you made that's online, and you were talking about, if I remember correctly, sort of lessons learned from dealing with viruses on Earth that would then help with understanding how you would do sample returns from Mars and making sure that the sort of sufficient containment. Is that the process that you've been through?
Yes, certainly. We learned a huge when we were working. Sorry, my microphone's just dropped away. When we were working,
live broadcast is all about.
When we were working on the Mars sample return recovery procedure, which I spent several years working on, then we had to look very carefully. We worked with the experts at Public Health England, who are at this moment working on the COVID-19 pandemic, as I'm sure you're aware, and they gave us a lot of advice on how to approach the vehicle when it hits the deck in the Utah desert, for example. So we learned a lot from them in terms of containment, and a lot of the techniques that we're now seeing every day in terms of biocontainment were things that we looked at several years ago in order to try and work out how we were going to keep these Mars samples from not contaminating the landing site.
And another question that's come in is around timeline. So I think you did touch on this in your talk, but just remind us, why will it only be 10 years or so before any possible samples that the rover collects can come back to the Earth?
Excuse me. Yes, absolutely. Well, those two launches, so there's 3 launches involved in Mars sample return. This one, which is the crucial first step. And then we've got 2 launches in 2026. We only actually get to the surface of Mars in 2028. And then we'll leave the surface of Mars again. The orbiting sample container will leave it on the Mars ascent vehicle in 2029, and then it takes a couple of years to get out of Mars orbit and then come all the way back to the Earth to 2031.
So another question, I think you may have touched on this as well, because you were talking about Martian meteorites coming to the Earth. How do they get off the surface of Mars in the first place and escape the gravitational pull of Mars? So that's coming from Lee Hulse, that question.
Yes, yeah, very sensible question, Lee, and definitely one that I was like, no, seriously, is that really a thing? So what happens? They have modelled this, that it's possible, and that is that, say, an asteroid hits the surface of Mars, and when you do when there's an asteroid impact, you have ejecta coming out from the crater. And those ejecta, if they have sufficient velocity, if the velocity is greater than the escape velocity of the planet, then they can actually go out of the orbit of Mars, and they can then go towards the Earth. And there is a slim chance that through the motion of the trajectory, then they will find their way towards the Earth and then through the Earth atmosphere. Incredible, but true.
It is remarkable to think about rocks from other planets being blasted away from those planets and landing on our own. I still find that remarkable. I remember when I first heard about lunar meteorites reaching us, I thought that was remarkable. And now I know we have Martian meteorites. So what a fantastic solar system we live in. So Lucy, I think we have taken up a lot of your time this evening, and we are so grateful that you could join us to give us your expert input and talk about the work that you're doing. I hope you can go off now and celebrate in whatever way you're able to do, and hopefully we'll keep in touch with you and find out about your work in the future as well. So take care, and thank you so much for joining us.
Thank you.
Brilliant. So I will hand over to Stuart now, who I think is talking to Stephen about the latest images, or the first images indeed, that have been coming down from the rover. So Stuart and Stephen, over to you.
Well, thanks, Lucy. Yeah, we're looking at the first couple of images from the hazard cameras on the Perseverance rover safely on the surface of Mars and Jezero crater. The image you're seeing now is from the rear right hazard camera. You can see in the lower right one of the 6 wheels visible on the surface of Mars, in addition to a few boulders or smaller rocks strewn on the surface there. And you can see the terrain relative navigation did steer the rover to a relatively safe landing site, relatively flat. You can see maybe in the upper right of this image from the front has cam, you might be able to make out one of the cliffs, maybe at the edge of the Delta deposit there. Not quite sure which direction we're looking. I'm not even sure, NASA knows quite yet. They're going to figure out the orientation of the rover over the next few hours to determine exactly which way the rover is pointing. But you can see, again, some interesting rocks there, interesting scientific targets. I'm sure scientists are already salivating to get the drill out and go explore some of those rocks. And just also a note, we're going to have more images from the rover later this evening, so stay tuned. These images are very low resolution thumbnails. In fact, the lens cover is still over both hazard cameras right now. So we'll get clear images and high resolution images later this evening if all goes according to plan, in addition to potentially the start of the playback of the entry, descent, and landing camera views that the rover recorded on the way down to the Martian surface. That'll be spectacular. We might see those tonight, if not tomorrow.
Great, thank you. Thank you, Stephen. That was fantastic. It's great to have that update, and great to be reminded that we can keep an eye for what's to come. Stuart.
Yeah, so we're almost at the end. I can't believe it. It's just feels like it's got started. I know. All that remains really is for us to say a big thank you to all of our speakers for being with us tonight. They've all made real time and effort to talk to us, and we're just so grateful and just so in awe of their achievements, what is going on. So thank you to all our speakers this evening, and also a big thank you to all of you for joining us in putting this together. You know, we miss AstroFest live dearly, and this is in some way, you know, helping us maintain the connection with all of you, because without you, AstroFest can't take place, and Lucy and I and all the rest of the team wouldn't get to have such a great weekend every February. So thanks for joining us. Lucy, back over to you.
Yeah, so I think all that's left to say now really is to close out on a short video, because of course you can see Mars in the night sky. So what a, you know, there's no better time to go out and look for Mars and reflect on the fact that after 7 minutes of terror, we've had the 5th rover placed on the surface of Mars, and we've taken the first steps towards collecting Mars samples to bring back to the Earth. So we're going to close out with a video from Greg Smybronsby to tell us how we can look for Mars in the evening sky. So let's listen to Greg, and thank you so much for joining us.
Thanks, Lucy. Now, it couldn't be a better night to go and see the planet Mars for yourselves. If you look to the southwest, you'll see a bright crescent moon, and above that, a red star. Now, that actually isn't a star, that really is the planet Mars. It's not as close to us as it was a few months ago, and the idea of seeing detail on its surface when looking through a telescope might be a little difficult. But there is one feature, famous, called the Syrtis Major. And to the right of that, on the extreme edge of the planet's disk, is the landing site of the Perseverance rover. So I'm going to wish you clear skies and hope that you see the planet Mars for yourselves.